So let's look at the following example that will deal with the kinetic energy and elastic potential energy of our oscillating system. Let's suppose that a certain spring that is attached to a mass of 0.5 kilograms has a spring stiffness constant of 25 newtons per meter and the oscillation has an amplitude of 0.15 meters. Now, knowing that information, we would like to calculate in part A the total energy of our system. In part B, find the potential and kinetic energy equations with respect to time. In part C, find the velocity when the mass is 0.06 meters away from the equilibrium position. And finally, in part D, find the kinetic energy at half the amplitude. So let's begin with part A. So, let's suppose that we compress our object, we let go, and that object begins to oscillate back and forth. Now, the total amount of energy of our object at any given time is given by the following equation. We simply take the kinetic energy of the object at that moment in time and we sum it with our elastic potential energy at that same moment in time. And that will give us the total energy that our mass has, that our system of objects have. Now, another way we can calculate the total energy is simply by recalling that if we compress our object, right before we let go of that object, all the energy is stored in elastic potential energy. So another way we can calculate the total energy is simply by taking 1/2 k times the amplitude squared. So this is the maximum elastic potential energy that is stored in our object. So we're going to use this equation to calculate our total energy. So 1/2 ka squared, where our k is 25 newtons per meter and the a is 0.15 meters. So we square this, we get 0.0225. We multiply that by 25 and by 0.5 and we get about 0.28 joules of energy is contained in the spring. When we compress that spring, a maximum displacement of 0.15 meters. Now, let's move on to part B. Find the potential and kinetic energy equations with respect to time. Now, before we examine the potential and kinetic energy equations, let's recall the general formula for our position function with respect to time. Now, it has the following formula, A times cosine of this quantity, where this is our angular frequency, this is the time, this is the phase angle, and this is our amplitude. Now, because we assume our initial position is when the object is fully compressed, that means our phase angle is 0. So we know this phase angle is 0, we know the A is 0.15 meters, and we can calculate our angular frequency by using the following formula. So angular frequency squared is equal to the ratio of the spring stiffness constant to the mass. So we simply solve for our angular frequency and we can calculate the angular frequency by taking the square root of k divided by m. So our k is 25 and our m is 0.5. So we divide 25 by 0.5, we get 50. We take the square root of 50 and we get approximately 7.1 radians per second is our omega. So now if we take this equation and we take our derivative of our displacement function, we will obtain our velocity function. So this is the general formula for the velocity function. Once again, our omega is 7.1. Our A is 0.15 and our phase angle is 0. So we're going to need to use these equations in just a moment. So let's actually plug in our 0.15 for the A and 7.1 for our omega. Now notice our negative times our negative 1 times our omega, 7.1 times our A, 0.15, we get negative 1.06, and this remains 7.1. So this is our equation for our position function with respect to time, and our equation for the velocity function with respect to time for our oscillating object for this example. Now recall the formula for our potential energy is equal to 1/2 kx squared. So we take this entire equation and we plug it into this equation, and we get the following result. So our k, which is given to be 25 times this whole quantity squared, we get the following equation. And this is our potential energy equation with respect to time. Now, this is our equation for kinetic energy. So kinetic energy is equal to 1/2 mv squared. So we know what the mass is, and we know what our velocity function is with respect to time. So we take this, we plug it into the v, we square that, multiplied by our mass, and we get this function. So this is our kinetic energy function equation with respect to time. So at any given time, we can plug in our time value and we will get what our energy is in joules of our oscillating object. So let's move on to part C. Find the velocity when the mass is 0.06 meters away from our equilibrium position. So, recall the following equation that we spoke of in part A. So this entire sum is equal to our maximum elastic potential energy when the object is fully compressed to its amplitude distance. So because this is equal to this, we can solve for the velocity and we get the following result. So we simply solve for this velocity. Notice the 1/2s will cancel, and if we rearrange, we get the following result. We see that the velocity is equal to this equation. So we know what k is, it's 25. We know what m is, it's 0.5. We know what a squared is, it's 0.15 squared, so 0.0225. We know what x is. X is simply, well, it's given to be this quantity. So we calculate that, we multiply, take the square root, and we get approximately 0.97 meters per second is our velocity of the object when the object is this distance from the equilibrium position. So now let's look at D. Find the kinetic energy when our displacement is half of our amplitude. So we're essentially going to calculate how much elastic potential energy our object has when it's found at that position, and then use this total constant energy, subtract our potential energy from this value, and that will give us how much kinetic energy we have. So we use our elastic potential equation, 1/2 kx squared, where x is 0.075, it's half of this quantity. Our k is 25, so we multiply, we get 0.07 joules. Finally, to find the kinetic, we simply have our total, we subtract our elastic, so total is 0.28 joules. Our elastic is 0.07 joules, and we get 0.21 joules of kinetic energy is found in our block when the block is found at a position of half its amplitude.